Well, since x plus 2 is a factor of f of x, we know that f of x, so therefore, this stands for therefore, f of x equals to, instead of this form, it is now going to be x plus 2 multiply another factor. But with this other factor here, this is when synthetic division is going to come in. So how do we find this other factor? Well, all we have to do is that we take the x values that give us the remainder 0 earlier, and we set it up, the synthetic division. So x equal -2, so it is a divisor on the left of the synthetic division. And on the right is going to be all of the coefficients of the function listed from left to right in this order. I mean, in the same order as given. So -1, +1, -6, 0, and then 32. Of course, we bring down the first number, which is the leading coefficient. So +1 stay here. -2 times 1 is -2. -6 plus -2 is going to be -8. -2 times -8 is +16. 0 plus 16 is 16. -2 times 16 is -32. 32 plus -32 is 0. Just one right here. -8. And then 16 right there. And the remainder, we don't have to worry about that. But what's going to go in the middle? What's going to go next to each of these numbers? Well, this is going to be x squared minus, and then x, and then plus 16. Well, why is it that it is x squared instead of x cubed? Well, because we already take the original function. We were able to crank out one of the factors that has the variable x raised to the invisible first power. So we include it in here, and because we already included it in here, that means that this other factor must have the degree 2, which is 1 less than the original one. So every time when you do synthetic division like this, after you find the first factor using the remainder theorem, always know that this other factor that you use synthetic division to come up with must have a degree that is 1 less than the one right before that. So you have degree 3 here. You find one of the factors of this given function, you put it in here, and this factor here has the degree 1. So of course the next one has to be the degree that is 1 less than this one. But anyway, we get x squared minus 8x plus 16. Now we have a quadratic expression here. So every time we have a quadratic expression, there are 3 ways that we can continue going about this. One is that we can continue repeating this whole process just for this one. 2 is, can we factor it out? Or 3 is, if we cannot factor it out, we have to use a quadratic formula. But this expression here is actually factorable because if you notice, x squared right here has the multiplicative factors of just x and x, so I put it right there. Since the leading coefficient is +1, I get to ask myself, what are 2 numbers that multiply together to give me +16, but also added together to give me back the second coefficient, -8? Well, that's going to be -4 and -4. And of course, this whole function f of x is equal to 0 earlier. So hey, we factor out the function f of x from this form all the way down to here. So we got 3 binomials factors multiplying together equal to 0. So we get to use the 0 product property, and we get to set each of these binomial factors equal to 0. So we got x plus 2 equal to 0. And since x minus 4 is repeating itself twice right here, I'm just going to write it once. And then, of course, you guys know how to solve for x from here. So this is going to be x equal -2, comma, x equal to +4 with multiplicity of 2. It is going to be multiplicity of 2 because x minus 4 repeating itself twice right here. And this is the final answer. So all of the rational roots of this function is x equals to -2 and x equals to 4. So the idea is that when you're given a polynomial function of degree 3 or above, the first step is to use the rational root theorem, crank out all of the possible rational roots, which is in the form of lowercase p over lowercase q, where p stands for all of the positive and negative factors of the constants, over q, which stands for all of the positive and negative factors of the leading coefficient. In this case, our constant is 32, and our leading coefficient is +1. Positive and negative factors of the constants are all of this, and the leading coefficient is all of this. And then take one factor in the numerator, set it over to each of the one at the bottom we get, and then we crank all of this out. And after you crank out all of the possible rational roots, it's only a matter of trial and error using the remainder theorem. And usually when you get to this chunk of word, you want to start with the lowest x values first, which is plus or minus 1 in this case. And then use the remainder theorem, take that x value that you select, plug it into the function to see if the remainder f of that f evaluated at that x value is going to be equal to 0. If it's not equal to 0, then you know that the corresponding binomial equation that is equal to 0 from that x value that you selected is not a factor of the function. And you keep going until you get to the x values that will give you the remainder of 0, which is x equal to -2 in this case. Then you know that the corresponding binomial expression that is equal to 0 is a factor of the function. From there, take the function and rewrite it into the form of the product of the factor that you found using the remainder theorem earlier, and another factor. Well, this other factor that you have to find is going to involve the synthetic division using the x values that you selected to come up with the remainder 0. After you do that, you will find that the quotient of the synthetic division is that other factor that you're trying to fill in the blank for. When you find out the quotient of the synthetic division, always know that from left to right, the degree of the other factor that you're trying to fill in the blank is going to be 1 less than the original degree, which is 3. And the reason why it is like that is because you already found a factor of x raised to the invisible +1 power plus 2. So that means that the factor that you're trying to fill in the blank by using synthetic division must have a degree of 1 less than the original one, which is 2. And yeah, from there just use zero products property and then solve for x, and that's how you find all of the rational roots of this equation.